Buckle up, everyone, because today we're taking a deep dive into a world that's, well, a little mind bending. We're talking quantum physics. Don't worry, we've got all the source material ready articles, research, even some of your own notes that you sent in, all to help us make sense of this fascinating and often very confusing topic.
And what's really cool about quantum physics is that it completely changes how we see reality. We're going down to the tiniest levels, atoms, and the particles even smaller than atoms. And at that level, things get really weird.
So, are we saying goodbye to the simple world of planets orbiting the sun and atoms acting like tiny billiard balls? Is that all out the window now?
Basically, yeah. Once you enter the quantum world, it's like a whole new set of rules. Things aren't so certain anymore. It's all about probability,
Sure.
and things can get this, be in multiple states at once.
Wait, hold on, multiple states at once. Okay, before we get too far down the rabbit hole, can you back up a sec? What exactly is quantum physics, and how is it different from the regular physics we all learned in school?
Quantum physics is, well, it's the study of how energy and matter behave at the absolute smallest scales. Like, imagine you're zooming in on something that looks solid. You keep zooming in until you see atoms, which are always vibrating, and then you zoom in even further to see the particles inside the atoms. At that level, the physics we used to just doesn't work anymore.
So you're saying my desk, which feels pretty solid right now, is actually, what, a bunch of vibrating stuff that might
Mhm.
not even be where it seems?
Exactly. In the quantum world, things aren't so clear cut. We
Yeah.
can't say for sure where something is or how it's moving. It's all about probabilities and uncertainties.
Okay, I think I'm starting to see why everyone says quantum physics is so weird.
Oh,
And this is where that whole Schrödinger's cat thing comes in, right? That thought experiment always kind of messed with my head.
Schrödinger's cat is a perfect example of one of the craziest ideas in quantum physics, something called superposition. Imagine a cat trapped in a box with, well, with a device that has a 50-50 chance of um, releasing a deadly poison. Until we open the box and look, the cat is in a superposition of states, meaning it's both alive and dead at the same time.
So it's not that we don't know if the cat's alive or dead, it's that it's actually both until we open the box. So is there like a universe where the cat's fine and another where,
Well,
well,
that's the mind-blowing part of superposition. It's not just that we're uncertain, it's that the cat, or any particle for that matter, actually exists in all those possible states at once until we measure it. It's only when we observe it that it chooses one state.
wow, okay, I'm already feeling a little dizzy. It makes you wonder how much we're not seeing in the world just because we haven't observed it yet.
And we're just getting started. If you thought superposition was wild, wait till you hear about entanglement.
Entanglement. Isn't that what Einstein called spooky action at a distance?
That's the one. He wasn't a big fan of the idea. But experiments have shown it's real. Entanglement happens when two particles, no matter how far apart they are, become linked. If you measure one particle, you instantly know the state of the other one, even if they're like light years away.
Wait a minute, faster than the speed of light. How is that even possible?
That's the big question. It's one of the most mysterious things about quantum physics, but it's definitely real. And it could even lead to new technologies like quantum computing and super fast communication.
Okay, so we've got particles being in multiple places at once, A and a D, they can talk to each other across the universe instantly. This is a lot to take in. What other crazy stuff is there in quantum physics?
Let's talk about wave-particle duality, which basically turns our understanding of light and matter upside down.
Yeah, I've heard about that one. Light acts like a wave A and D, a particle, right? But
right.
isn't light, just light?
It's not that simple. Light, and even things like electrons, can act like waves or are particles, depending on how we look at them. There's this famous experiment, the double-slit experiment, where particles create these interference patterns like waves do. But if we try to see which slit the particles go through, they suddenly act like particles again.
So just by looking at them, we change how they behave. It's like they know we're watching.
You got it. In quantum mechanics, the observer isn't just passive. The act of observing actually affects the outcome. And that leads to some really deep questions about what reality even is.
So this is blowing my mind. How do physicists even begin to understand all this craziness? Is there like a framework that helps explain these weird quantum phenomena?
There is. It's called quantum field theory, or QFT for short.
Yeah.
And get this, it combines quantum mechanics with Einstein's theory of special relativity.
Wow, two of the most mind-bending theories all rolled into one. So do I need a PhD to understand this QFT?
You don't need a PhD, but it does require thinking about things in a whole new way. Instead of picturing particles as little solid balls, QFT says they're more like excitations in fields that spread out through all of space.
Excitations and fields. So more like ripples in a pond than tiny marbles.
That's a good way to visualize it. Imagine a still pond. If you toss a pebble in, it creates ripples that spread out. In QFT, particles are like those ripples, and the pond is a field that exists everywhere.
So what we think of as individual particles are actually just disturbances in these underlying fields.
Exactly. And here's the crazy part. This means that even when it seems like there's nothing there, empty space, it's actually buzzing with activity from these quantum fields.
Wow, okay. This is really changing how I picture, well, everything. So if everything is fields, where does mass come from? How do things get heavy?
Uh, that's where the Higgs field comes in. But you know what? I think we need to take a break and pick up this fascinating thread in part 2 of our deep dive.
Okay, we're back. And I'm still trying to wrap my head around that whole empty space isn't really empty thing. Before the break, you mentioned the Higgs field. Is this where we finally figure out how things get their mass?
You got it. The Higgs field is like the VIP of quantum field theory. It's what gives particles their mass.
So let me get this straight. Without the Higgs field, would everything just be zipping around at the speed of light, like weightless?
Exactly. The Higgs field is like, imagine running through a pool filled with molasses. It's tough to move, right? That's kind of what the Higgs field does to particles. Some particles get really bogged down and gain a lot of mass, while others just kind of skim through and stay light.
Okay, that makes sense. But is this Higgs field just a theory, or have scientists actually seen it?
It's not just a theory anymore. Back in 2012, scientists at CERN, that giant particle accelerator in Europe, they found something pretty amazing. They discovered the Higgs boson.
Oh, yeah, I remember hearing about that. But I had no idea it was connected to, like, how things get their weight.
It was a huge deal. Finding the Higgs boson was like finding the missing piece of the puzzle. It proved that the Higgs field exists and helped explain why some particles have mass and others don't. It even won Peter Higgs and Francois Angot the Nobel Prize in Physics.
Wow, that's incredible. And this all ties back into that quantum field theory, right? The one that combines quantum mechanics and relativity.
Right. QFT doesn't just explain the Higgs field, it also explains the fundamental forces of nature.
Forces, like gravity and electromagnetism, are those what you mean?
Exactly. We know of 4 fundamental forces: gravity, electromagnetism, the weak force, and the strong force. And the cool thing is QFT explains 3 of them: electromagnetism, the weak force, and the strong force, all through the lens of quantum mechanics.
So what about gravity? Does that fit in with QFT too?
Well, that's the million-dollar question. Combining gravity with quantum mechanics has been a bit of a headache for physicists. It's like trying to fit a square peg into a round hole.
So are there any scientists working on, like, solving this problem?
Oh, absolutely. There are tons of brilliant minds all over the world trying to figure out how to unify these 2 big theories. String theory and loop quantum gravity are 2 of the leading contenders.
String theory, that's the one that says everything is made of tiny little strings, right?
That's the one. String theory says that the fundamental building blocks of the universe aren't particles, but these tiny little vibrating strings. Different vibrations create different particles and forces.
Okay, I kind of get it. And what about that other one, loop quantum gravity?
Loop quantum gravity takes a different approach. It suggests that space itself isn't smooth and continuous, but it's actually made up of these tiny, discrete chunks, kind of like pixels on a screen.
So, like, space is pixelated? That's a pretty wild idea.
It is. Both string theory and loop quantum gravity are still being developed, but they're both exciting possibilities for figuring out a theory of everything.
A theory of everything? I like the sound of that. It's pretty amazing to think that we might be getting closer to understanding, like, the deepest secrets of the universe. But all this talk of forces and strings and loops, does any of it actually affect us in the real world?
Absolutely. Quantum physics isn't just theoretical, it's all around us. A lot of the technology we use today wouldn't exist without it.
Really? Like what? Give me some examples.
Well, think about medical imaging. MRI machines, the ones that give us those detailed pictures of our insides, they use a quantum phenomenon called nuclear magnetic resonance.
Wow, so those MRI images are thanks to quantum physics.
They are. And then there are semiconductors, the tiny chips that power our phones, computers, pretty much all our electronics.
Yeah.
Those wouldn't exist without our understanding of quantum mechanics.
So every time I check my phone, I'm actually using quantum physics.
Yep. And don't forget about lasers. They're everywhere. From barcode scanners at the grocery store to fiber optic cables that send information super fast, and those rely on the quantum phenomenon of stimulated emission.
It's crazy to think that something so strange and mind-bending is also so practical.
It's pretty amazing.
Yeah.
And even something as basic as GPS navigation, it relies on atomic clocks, which also use quantum principles for super precise timekeeping.
So quantum physics is way more than just these weird ideas. It's actually shaping our world in some pretty big ways. But there's one more thing I wanted to ask about. The many worlds interpretation. This is where quantum physics starts to sound like, I don't know, science fiction.
Yeah, the many worlds interpretation is definitely one of the most mind-blowing ideas out there. It basically suggests that every time a quantum measurement happens, the universe splits, creating a separate branch for every possible outcome.
Hold on, are you talking about parallel universes? Like every time I make a decision, there's another universe where I made a different choice.
That's the basic idea. Going back to that Schrödinger's cat. It's not just that the cat is both alive and dead inside the box, but that there's one universe where the cat lived and another where, well, it didn't.
So there could be countless versions of ourselves out there, living out every possible version of our lives.
That's what the many worlds interpretation implies. Of course, we can't actually travel between these universes or even prove they exist, at least not yet.
Whoa, this is getting pretty deep. But it's fascinating to think about the possibilities.
It definitely makes you question everything you thought you knew about reality. But it's important to remember that the many worlds interpretation is just that, an interpretation. It's one way to try and make sense of the weirdness of quantum mechanics.
So even the experts are still debating what it all means.
Exactly. We've come a long way in our understanding of the quantum world, but there's still a lot we don't know. And that's what makes it so exciting to keep exploring.
Well, I think our brains have had enough quantum weirdness for one day. We've covered superposition, entanglement, the Higgs field, even parallel universes.
It's been quite a journey. And I think it shows just how much quantum mechanics is changing how we see the universe and our place in it. But, we have a lot more to discuss. Maybe we can continue this deep dive in part 3.
Okay, so we're back, and I gotta say, after all that talk about parallel universes, I'm not sure I'm fully back in this one yet.
Yeah, it definitely makes you think, doesn't it? All those possibilities, it's kind of mind-blowing.
It really is. But even if we, you know, can't actually prove those other universes are out there, it's just incredible that physicists are even considering these ideas. I mean, it shows just how much quantum mechanics is shaking up everything we thought we knew about, well, about reality.
It really is a huge shift. For centuries, people thought the universe was like a giant clock, everything ticking along in a predictable way. But quantum mechanics says, well, not so fast.
So are you saying there's no such thing as cause and effect anymore? Is it all just random?
Not quite. Quantum mechanics doesn't say that cause and effect doesn't exist, but it does introduce this element of probability, of uncertainty. It's like, yeah, there are rules, but there's also this element of chance, of randomness mixed in.
Okay, so it's not total chaos, but it's not like totally predictable either. It's
Yeah.
somewhere in between.
Yeah, that's a good way to put it. And this whole probability thing, it has some really interesting consequences.
Like what? Besides, maybe having infinite copies of ourselves out there making different decisions.
Well, think about how we see reality itself. In classical physics, we always assume there's an objective world out there. It exists whether we're looking at it or not. But quantum mechanics suggests that the act of observing, of measuring, actually plays a role in shaping reality.
Wait, are you saying that our consciousness, like our minds, actually influence how the universe behaves?
It's a pretty wild idea, right? And it brings up all these philosophical questions about what consciousness is, what role it plays in the universe.
I can definitely see why some physicists might start thinking about philosophy after dealing with all this quantum stuff. But I want to bring it back down to earth a bit. We've talked about how quantum mechanics is weird, counterintuitive, even potentially universe splitting. But what's next? What are the big questions that physicists are still trying to figure out?
Well, as we touched on earlier, one of the biggest challenges is figuring out how to combine quantum mechanics with general relativity. These are two incredibly successful theories, but they describe different aspects of the universe. Quantum mechanics is all about the very small, and general relativity is about the very large. And so far, we haven't been able to fit them together perfectly.
So finding a theory of quantum gravity, is that like the holy grail of physics right now?
You could say that. String theory and loop quantum gravity are two of the main contenders, but we're still a long way from having all the answers.
Are there any other big mysteries besides this whole unification thing?
Oh, there are plenty. For example, we still don't fully understand dark matter and dark energy. I mean, they make up the vast majority of the universe, but we still don't know what they are exactly.
It seems like every time we answer a question in quantum physics, 10 more pop up.
That's what makes it so fascinating.
Hmm.
Science is a never-ending journey, and the quantum realm is full of mysteries waiting to be uncovered.
It's pretty humbling and a little bit exciting, too. So, for all those listening who are just starting to learn about quantum physics, what advice would you give them?
I would say don't be afraid to embrace the weirdness. This is a realm where the old rules don't apply, so be prepared to challenge your assumptions. The more you learn, the more you realize how much there is to discover.
That's a great point. Well, we've covered a lot of ground today: superposition, entanglement, the Higgs field, even the possibility of parallel universes. It's been a wild ride through the quantum realm.
It has been. But, even with all the strangeness and mystery, I think the most important takeaway is that we're living in a universe that's far more complex and wondrous than we ever imagined.
So, to all our listeners out there, keep your minds open, keep asking questions, and never stop exploring. Who knows, maybe someday you'll be the one to unravel the next great mystery of the quantum world.
And until next time, keep exploring the infinite possibilities of the quantum realm. This is The Deep Dive, signing off.